Good day, everyone. This is Paul Rottenberg with Fire Stats. Welcome. This is a free video that hopefully will get you interested in our subscription content. We'll do some stuff in Excel here, and I'm not going to explain in detail the things I'm doing in Excel to get to the point that we need to get to in explaining percentiles. But hopefully you'll understand that, of course, if you subscribe to the site, then you'll get access to a lot of videos, some as short as a couple of minutes and some as long as 10, 15, 20 minutes or longer, that explain certain things about how to do stuff in Excel that will be helpful in performance measurement and data stuff in fire departments. So without further ado, and I will say that there's a shorter video for folks who just want to get a sense of, hey, what do the short videos look like, and what's some of the stuff that I can learn off of this site. So to talk about percentiles, the best way to really explain it is to simply just work with some data and do some demonstration. So what I want to do is I want to work with some response times here. So I'm just going to calculate some response times here from some random data. I got about 10,000 records here, exactly 10,000 records that I've randomly selected from another data set and stripped out all the stuff that we don't need. And so here's some response times. And because they're in random order, they're not in order by date or time or the amount of response time. So they truly are random. What I'm going to do is I'm going to grab, strip out the values here. I'm going to grab 10 of these values here, 10 response times. There we go. And I'm going to block them, and I'm going to drop them right here. And then I'm going to sort them and put the longest one at the top, and then I'm going to put them in rank order. So that's 10 and 9, and so I'm going to have to fix that format there. There we go. And all right, so now I've got my 10 values here that are response times that I want to calculate percentiles for. Now, typically, fire service tends to talk about 90th percentiles because of the influence of NFPA 1710 and to a lesser degree 1720 and certainly 1221 on the dispatch side, although 1221 refers to some other percentiles besides the 90th percentile, but we're going to focus on the 90th. Now, it just so happens that the data we're working with, the 90th or the ninth value here is 6 minutes. It's totally meaningless that it's 6 minutes. It's just totally random that it happened that in this sample data set, the ninth value was 6 minutes. Now, if I was in a classroom and I asked a bunch of folks in the fire service in my class, I said, hey, what's the 90th percentile in this data set? Pretty much everybody in the room would say it's that one right there. It's 6 minutes because that's the ninth value out of 10, and 90% of 10 is 9, so 90% of the data is what they would say is at or below 6 minutes, and they would say that that is the 90th percentile. And I would say, well, okay, maybe. And then people would look at me like, well, what do you mean maybe? And I'd say, well, it depends on your definition. And so what we're going to do is we're going to talk about the definitional stuff and we're going to calculate it. So on the definitional side, let's start with maybe a common and basic definition. So this is from the College Board's website. So if you were taking the SAT or you had a kid who was taking the SAT, they would get a raw score and then they would get a percentile ranking. So let's see what the College Board, that they test about 1 million kids a year, what they say. They say a student's percentile rank, I'm reading over here under percentiles, right? A student's percentile rank represents the percentage of students whose score is equal to or lower than their score. For example, if a student scores in the 75th percentile, 75% of a comparison group achieves scores at or below that student's score. So essentially what they're saying is, if we were talking about the 90th percentile, then we would say, well, 90% of the data is at or below 6 minutes. And therefore, the 90th percentile is 6 minutes. And, we could just simply, say, all right, well, that argument is settled. And I would say, well, maybe and maybe not. So why would I say maybe not? Well, let's say we look here. I'm going to drag in another reference over here into the screen. This is Wikipedia. Now, people love to make fun of Wikipedia, and there's certainly a lot of garbage in there, but there's also a lot of credible stuff. There's a lot of people with a lot of talent putting things here, and so let's talk about it. So here, a percentile or centile is a measure used in statistics indicating the value below which a given percentage of observations in a group of observations falls. Okay, let's look at that closely again. A percentile is a measure used in statistics indicating the value below which a given percentage of observations in a group of observations falls. For example, the 20th percentile is the value or score below which 20% of the observations may be found. Now, if you read down here, what you'll find out is that there's a fairly good explanation of different ways of calculating percentiles. And in fact, this Wikipedia article identifies 8 different methods for calculating percentiles. But the thing to focus on is the very beginning here with the definition, because the definition says essentially that the 90th percentile in this data set would be the value below which 90% of the data falls. So the value under which 90% of the data falls is actually the value associated with rank order 10. So if I were to use that first, and what arguably might be said to be the most common definition of percentile, then looking at the small data set, I'm going to tell you that the 90th percentile is 742 and not 6 minutes. Now, if you and I are looking at this and we're using different methods of calculating, then we're going to come up with 2 radically different answers. So that's kind of a problem. Now, let's take a look at another reference. So this is, you can see up here, this is from NIST, the National Institutes of Standards and Technologies. They have a, essentially it's a statistics handbook. And if you look here, it says the pth percentile of a data set is defined as that value, I'm reading here under description, as that value where p% of the data is below that value and 1 minus p% of the data is above that value. For example, the 50th percentile is the median. The default method for computing percentiles in data plot is based on the order statistic, the formula is, and so forth and so on. So just reading that again, the pth percentile, so let's say the 90th percentile of a data set is defined as that value where 90% of the data is below that value. Okay, so essentially NIST is saying the same thing that Wikipedia is saying as far as its first explanation or definition. Now, if you scroll down here, there's a little note, and it says here, note that there are a number of other ways of calculating percentiles in common use. Hidman and Fan in 1996 in an American Statistician article evaluated 9 different methods. We'll refer to these as R1 through R9 for computing percentiles, and so forth and so on. And then down below, there's some discussion of that. So NIST is saying there's 9 different ways of doing it. Wikipedia says there's 8 different ways of doing it, and the College Board is explaining one way of doing it. But the first methods that Wikipedia and NIST describe would yield, in this data set, a 90th percentile of 742, whereas the College Board would yield a 90th percentile of 6 minutes. So that's a little bit confusing. Which one do we choose, and how do we choose it? Well, now it's going to get a little bit more confusing. So let's say, for example, I used a formula in Excel. I said equal sign percentile, super easy. And I blocked all this data, and I said, hey, give me the 90th percentile there. Well, it's going to yield some garbage. There we go. Excel says the 90th percentile. So I said equal sign percentile, and I used that data range, and then I used 0.9 or the 90th percentile as in the syntax here. And we'll go into the syntax a little bit later in this video, but Excel's giving me an answer, 6 minutes and 10 seconds. 6 minutes and 10 seconds isn't even in this data set. So why is Excel telling me this? Is it broken? No, it's not broken. It's using a different way of calculating. So we've just looked at 2 different ways of calculating, and neither of those actually explains what Excel is doing. And chances are, if you're doing this in Excel, so you want to understand how and why it's working like this. So what I'm going to do is, instead of using 10 values here, I'm going to use the first 13 values. So I'm going to grab 13 data points here and drop them over here. And then I'm going to put them in rank order. Well, actually, first I got to rank them. So I got to sort them. So go up to data and sort these in descending order. And then I'll make this one number 13 and this one number 12. And I'll block those and I'll fill them down and fix this seeming junk here by changing all those formats. And there we go. So we have 13, 12, 11. No, that's not what I wanted. 13, 12, 11, 10, 9, 8, etc., etc. Perfect. Okay, so our highest value is rank order 13, and then rank order 12, and 11, and 10, and 9. So if I was just looking at this data set and I said, well, where's 90% of the data? Well, using the rank orders as the basis, what I would do is I would say, well, let's take 13 data points and multiply it by 0.9, or 90% of 13, and that'll tell me what's the rank order that I'm looking for. So I want to find the value, the response time that corresponds with 90% of 13. And so this looks a little garbagey, but it's just a formatting issue. So the answer is that I'm looking for the value associated with rank order 11.7. Well, there is no rank order 11.7, is there? There's rank order 12 and there's rank order 11. Well, it turns out that there actually is a rank order 11.7. And it happens to be 70% of the distance between the value associated with rank order 11 and the value associated with rank order 12. So it's 70% of that distance. So let's do this. Let's take the value associated with rank order 12 and then we're going to take the value associated with rank order 11 and we're going to figure out the difference. We're going to go equal sign. We're going to take the rank order 12, subtract rank order 11. It's 13 seconds is the difference. So what we want is we want 70% of the distance, right? So we're going to say 0.7 is going to be our multiplier. And so what we're going to do is we're going to say equal sign, and we're going to take that 13 seconds and multiply it by 70 seconds. And we're going to come up with an answer here that is 9 seconds. So 9 seconds is 70% of the distance between these two values, which would, if we added it to 729, which is the value associated with rank order 11, then we would get the value of rank order 11.7. So let's just do that. Let's just go equal sign, and we'll take the value associated with rank order 11, and we'll add it to 9 seconds, and we'll come up with the answer, which is 7 minutes and 38 seconds. So 738 is the 90th percentile in this data set where there are 13 values and these are what they are. Now the reality is that nobody cares what these are. These bottom 10, they don't feed into the equation. And this top one doesn't feed into the equation either. So we're really only figuring out what the distance is between these two to come up with rank order 11.7. And this process is called linear interpolation. And it's a statistical term, but it's important. It's the process of finding in a straight line the distance between here and here and any given point on that line. So rank order 11.7 again is 738. So let's use Excel and see what Excel says. Well, I'm going to go equal sign percentile, and notice that what happens is Excel offers me 3 different formulas. Percentile.exe, percentile.inc, and percentile. And they're actually only 2 different formulas. There's INC and the one with no suffix, just percentile. Those are the same. And then percentile.exe is different. So if I did percentile.inc, which is the same as =percentile, and I'm prompted for a data array, so there's my data, and comma, what Excel's prompting me here for, which is called K, is a statistical term, which just means the percentile that I'm looking for. So I'm going to drop 0.9 in there and hit enter. Then I'm going to get an answer, and the answer is 739. And that 739 is different than this 738. Well, why is it different? So we're going to have to explain that. And it's going to take a second, so bear with me. Here's what we're going to do. I'm going to show you what that formula is. I'm going to write the formula here and explain how it works. So Excel's looking for a rank order, and its formula is n, which is the number of values, equals the percentile, or the percentage over 100, times the count minus 1 plus 1. So using the 90th percentile as our example, we'll say n equals 90 over 100 times n minus 1 plus 1, or 0.9 times, and what's our n? Well, our n happens to be 13. So what we're really doing is we're saying 0.9 times 12 plus 1. And really what's happening is the 0.9 times 12 is happening in the brackets. So let's do this. We'll say equal sign 0.9 times 12 to come up with the answer. And the answer is 10.8. So going back over here to our description, it's actually 10.8 plus 1, which equals 11.8. So in the percentile.inc, wow, that's a terrible circle I just drew. Excel is telling us that the percentile, the 90th percentile, is going to be the value associated with rank order 11.8. See how we got there? Okay, so rank order 11.8, if we were to simply change this to looking for rank order 11.7 to rank order 11.8, I'll just change that to a 0.8. And notice that Excel recalculates this and we get 739, which matches that up there. So we'll change that back to 0.7, and we've got 738 using traditional linear interpolation, and we've got 7 minutes and 39 seconds. So 738 traditional, 739 using the percentile.inc formula. And so let's try another formula. So this is Excel percentile.inc. And so now what we're going to do is we're going to try percentile.exe and see how that varies. So if I were to say equal sign percentile.exe, left parentheses, and I block this array of values and comma 0.9 for the 90th percentile, and I hit enter, then let's see what kind of an answer we get. 754. Okay, so now why is that? Well, let's take a look at how the percentile.exe formula works. So percentile.exe, grab my pen here. The formula is n equals p over 100. Actually, you know what? I need to move this a little bit, so I'm going to block all this stuff and get rid of it, and I'll start over here to the left a little bit. So we're going to say n equals p over 100 times n plus 1. So in other words, n equals 90 over 100 times, in this case, 13 plus 1, which means that 0.9 times 14 gives us our answer. So what's 0.9 times 14? Well, let's just go over here and do the math. Equal sign 14 times 0.9 is 12.6. Okay, so we're essentially saying that we want to interpolate to the value associated with rank order 12.6. So let's put in 12.6 here, and that's the answer using percentile.exc. So the value associated with rank order 12.6 is 60% of the distance between 802 and 742. So if I were to say, hey, let's take 802 and 742 and we'll find the difference. So we'll take 802 and we'll subtract 742. That's 20 seconds. And we're looking for 60% of the difference, remember? So we're looking over here, 12.6. So I'm going to say 0.6 there, and I'm going to say, okay, take the 20 seconds and multiply it by 0.6. That's 12 seconds. And let's take the 12 seconds and we're going to add it to the value associated with rank order 12, which is 742, and we get 754. And is that the number that we were working with over here? Why, yes, it is, 754 and 754. So we've gone through traditional linear interpolation, which I showed you at first, which is right here. And then we took apart percentile.inc, and then we took apart percentile.exc. And notice that percentile.inc, which again is the same as equal sign percentile formula-wise, is lower than percentile.exe. And essentially the reason is because percentile.exe includes 100th percentile and percentile.inc does not. So when I do statistics using Excel and I calculate percentiles, I always use equal sign percentile, which is the equivalent of this one right here, percentile.inc. What makes percentile superior is it has the fewest keystrokes. So if I just go equal sign percentile, left parentheses, I'm prompted for the data array and the K, and I will get this answer here associated with percentile.inc. Now, in a small data set, these differences can be significant, but in a large data set, they are irrelevant. So the thing is that a lot of times fire departments are doing percentile calculations on things like effective response forces on high acuity, low occurrence events like structure fires with full first alarm assignments. And so what's going to happen is you're going to have inherently small data sets, and you're going to have the potential for a lot of variation in the answers depending on which formula approach you take. But if we were to look at, for example, all of these 10,000 response times, I could say equal sign percentile.exc, left parentheses, block all 10,000 of these, and put in 0.9, and I get 1228. And if I go equal sign percentile.inc, left parentheses, and I block all these values and I put in 0.9, I'm going to get the same answer. Well, pretty darn close. That's just a mathematical quirk that they came off a little bit different. In fact, it's almost certainly a rounding issue. And the reason it's almost certainly a rounding issue is if I were to insert a column here, and let's say I take these rank orders from over here, and I fill them down, the interpolated values, given that we're talking about 10,000 records here, let's go to value associated with rank order 9,000 and see what it is. So here's 9,000. We got to sort these in order. Okay. So let's sort those in order. Get rid of those. And we'll make this rank order 10,000 and rank order 999. Autofill down. So we're going to go down to rank order 9,000 and we're going to see what value is corresponding with rank order 9,000. And here we go. There's the thing. Is you see a whole bunch of 1028s right there, and then a whole bunch of 1027s, because there's just a finite number of times that we can have in this data set, and a bunch of 1026s and 1025s. So the breakover point between 901 and 9,000 happens to be 1 second, according to this data, which is why those two calculations yielded different answers. It just happened that we had a breakover there, but in most instances, you'll see multiple values at the same level. So here's 1029. There's looks like 6 or 7 of those, and then 1028, a bunch of those, 1027, a bunch of those. And as we get down into, let's say we go down to the 6,000 range, we'll probably see a lot of recurring values. So here in the, let's call this the 3,400 range. We've got 505 starts here, and we got a whole bunch of those. And it's because there's a finite number of times. So there are going to be lots of times that are the same. So in a large data set, again, it doesn't really matter. We're going to get pretty much the same answer over and over again. So if we go equal sign percentile dot exe, and we take this data array, put in the 90th percentile, we get 1028, and if we did equal sign percentile, take the data array and 0.9, and we get, I believe it was 1027. Okay, and again, it's just because of that breakover. So statistically, for all practical purposes, there's no difference between the two. Just happened to be that they were breaking over there. So hopefully this explains the fact that there are several different ways of doing this. And the most important thing is that you pick one and be consistent in which formula you're going to use. So if you're using Excel, you're really only offered 2 choices, percentile.inc and percentile.exe. And again, INC yields a lower answer than EXC. I think it's statistically more conservative, so it's the one that I use. But again, the most important thing is to be consistent so that when you do it period after period, you're using the same formula, you're coming up with the same answers, you're using the same size yardstick. And when you pass this off to the next person in your organization, not only do they know what they're doing, but they know why they're doing it. So hopefully this has been helpful, and hopefully you'll go back to the website and subscribe. There will be a lot more videos like this that will go into depth on certain types of calculations that you're likely to use and how and why, plus lots and lots of tips and tricks on how to use Excel effectively in a fire service environment. And so if you made it to the end here, then I really do appreciate it. And thanks so much.